Keep it casual.
Okay.
So, I'm here in San Francisco at the office of Skymind, and in front of me it's the CTO of Skymind. So you're one of the founders?
Yes.
Okay, so who's CEO then if you're CTO?
So my co-founder is Chris Nicholson.
Okay.
He's actually from the press.
Okay.
Yeah.
Is that the guy in Hamburg? No.
Yeah, so no, that's Max. So
okay.
So Chris, I met at a hacker hostel in San Francisco.
Okay.
So about 5 blocks from here.
Okay.
We were 10 feet away, sleeping 10 feet away in different beds.
Okay.
And yeah, we met at a hostel and yeah, kicked it off. So.
Okay.
Yeah.
So was this the time where you had the idea to found Skymind?
Yes.
Okay.
So basically so Deeplearning4J started in 2013.
Okay.
And Skymind started in 2014.
Okay. And so you basically started first with a project and you implemented some framework and afterwards you
and then after that the company, because I was very familiar with open source because I was a big consumer of of Spring and a lot of that, and I saw how that all got started. And, you know, Linux, Red Hat, you know, so I want to do something similar for deep learning.
Okay. So, but to my knowledge, you don't have 5 PhDs of MIT.
No, we have 5 PhDs, but they're not from MIT, no. Okay. We have one guy from Stanford who used to work under Sebastian Thrun, though.
Okay.
Yeah. So.
But how did you actually learn all that stuff?
So I actually did 3 startups prior to Skymind.
Okay.
And a lot of what I did was machine learning, ironically. It was all in Java.
Okay.
And so I learned machine learning by working on projects and selling software.
Okay.
And so Skymind was just a natural extension of that.
Ah, okay.
But I learned deep learning specifically by building Deeplearning4J.
Okay, and then you basically came to know that there is no tensor library for Java, and then you write.
Right, and so and so mid 2014, you know, I tried all the different matrix libraries on the Java virtual machine.
Okay.
And none of them were fast.
Okay.
So and they were also heavily restricted compared to NumPy.
Okay.
And so that's when I decided to build kind of the NumPy for Java.
Okay. Okay. Awesome. Is somebody using NumPy as a standalone product without Deeplearning4J?
So a lot of Alibaba.
Ah, Alibaba. Okay.
Alibaba. So a lot of lower level folks just use ND4J as a matrix library and for compute.
Okay.
And they like it for that. So HPC applications, research in academia, which a lot of Java tends to use ND4J.
Okay. So a lot of things are going on in Deeplearning4J. Whenever I need a Skymind employee, tons of things are new. So what are the top 3, 5, what is things at the moment?
So right now, I would say my favorite thing is SameDiff. This is on purpose. There's tons of automatic differentiation libraries. Ours, you know, it's like, well, it's another one, but it's, you know, it's in the JVM. And so our PyTorch-like API that'll be coming out soon.
Okay.
We also have, I would say, integration, our new parameter server that just came out, very similar to MXNet and all the other frameworks, but it uses Aeron, which is a lot faster than gRPC. Okay. It's also a lot more stable for latency because it came out of Java Financial Services, where there's a lot of kind of low-level Java C++ galleys.
Okay.
Those are, I would say, the top 2.
Okay.
Right now.
Top 2. And what about the Keras integration?
So Keras integration, you know, Keras 2.0 came out. We have that. We support that now. Import's still not 100% done though. So that's still a work in progress. But one feature that a lot of folks don't know about is workspaces.
Okay.
So this is something only we have, but it's basically the ability to automatically figure out how much memory you need and only allocate that up front. And we basically minimize garbage collection because of that. So we basically found a way in a dynamic, a garbage collected language to replicate very similar feature that C++ has for our tensor library. And so that allows us to do GPU resource management as well as CPU. And it's all out of the box.
Okay. How do you interact with GPUs?
So a lot of what we do is we have ND4J, which is our Java library, but underneath that is libND4J, which is all straight C++.
Okay.
And so what we do is we control the allocations from Java. And we do basically, it's called an LRU cache. We do an LRU based implementation of GPU memory, GPU memory eviction. And so we use that to control what memory is allocated on the GPU. And then from that, you can also control your environment, like your GPU RAM, visible GPUs, and all your other operation stuff that you might want to do. And so it's all Java native interface based.
Okay.
And at the core of that is something called Java CPP, which the Mahout project uses it among others. Also, Twitter's Vine used it at one point for its kind of automatic Java to Java native interface to C++ automatic transpilation. So it's basically a very specialized swig for the JVM. And so we use that for all of our off-heap memory management as well as all of our native integrations.
Okay, awesome. And what type of layers do you support out of the box?
So out of the box, we're supporting GANs now. We have various kinds of output layers. We have YOLO now. The next thing we'll be implementing is CTC soon for audio and speech.
Okay, and of course.
And then we support like different kinds of CNNs, ResNet. Basically, you can build any kind of neural net with our computation graph API though. Okay.
Can you tell a bit more about the computation?
So the computation graph, as you know, is you have each layer as your vertices, and your layer connections are your edges, right? And so a lot of you can't just build a multi-layer network, multi-path network using a straight feed-forward architecture. So we have a multi-layer API for that, for just simple, for a lot of beginners who just want a feed-forward CNN or whatever, they're not, they don't want all the complexity of, the computation graph. And so we just give them a simpler API. But the computation graph is if you have, if you have something crazy like an embedding layer followed by two different diverging paths, like a lot of NLP neural nets have that. So from that you use our computation graph. And so for a lot of the new flexible architectures like ResNet, BGG, and a lot of that, then you would typically use a computation graph, the computation graph API, and that it's kind of a higher level hybrid of TensorFlow with Keras, and so we're more flexible than Keras if you use the computation graph API, but you have to implement a lot of the layers yourself.
Okay. So for example, if I want to add the differentiable neural computer,
yes,
that would be possible on the computation.
It would be, and what we're going to do is with our computation graph API, we're actually going to combine that with SameDiff, where you'll have an autodiff layer, and then you can specify what you want. And then so you'll be able to combine like the existing DL4J stack, if you have a reshape layers, combines multiple paths, you can do all the same stuff with a higher level API, but then you can add automatic differentiation for things you're missing for implementing layers.
Okay. Can you tell a bit more about automatic differentiation?
So automatic differentiation is at its core, TensorFlow, Theano, Torch, all these libraries support it. And at its core, how it works is you have, instead of layers like the DL4J version is, you just have matrices or tensors, ND arrays, with operations connecting to other ND arrays, outputting an ND array. And so at its core, you have that kind of computation graph, which is lower level. And then, based on that graph, what you can do is you can go all the way to the end with the feed forward, and then you start backwards. You usually with a scalar, like a scalar function, like sum the whole thing to get the loss, right? You start from that, and then you work your way backwards. And so what you do is you start with a scalar 1, because the derivative of a scalar is 1, right? And you work backwards from that using the chain rule across the graph. And what you do is in order to determine execution order, you use topological sort. And from that topological sort, you get the execution order, and you get the chain rule, which gives you automatic differentiation.
Okay. So that means I don't have to care anymore about this.
Right. The backprop, which is typically the hard thing to write.
Yeah.
Most papers nowadays don't even give you the backprop math anymore. They rely on the fact that you have an automatic differentiation framework now.
Because it's like per definition, it's always working. And
it's always working. It's just there. And you typically rely on a framework now because the backpropagation for GANs is very complicated apparently. For example, like there's a lot of considerations when writing real backwards operations too. Like you have to reshape things, you have to broadcast them. Like there's a lot of shape operations and a lot of manipulation you don't want to have to think about. Like what's the right matrix order for this? If I have to rearrange it, like do I have to transpose this? I don't want to have to think about that. And so so these autodiff APIs take care of that as well as what you'd normally think of as a derivative.
Okay. And after that, of course, you have to optimize.
Yeah. So then there's then the next step of the computation graph is to then take redundant operations, collapse them, figure out do I need to duplicate this memory or not. And so TensorFlow and a lot of these other frameworks have that built into it, and we will as well.
Okay. So that's in your roadmap.
Exactly.
Okay. And regarding training, so you are supporting gradient descent?
Yes. So also we support nearly everything: Atom, RMS Prop, and Atom now, Nesterov's. all the updaters you'd think of. We have all the new activation functions like Selu as well.
Okay.
So a lot of that in there will run just like what you would in TensorFlow.
Okay.
But then the novel thing that DL4J does, and I would say the main focus is the Spark integration, Kafka, things like that, where you already have this infrastructure in place, and you want to run you just want to run distributed training.
Okay.
Right, and so the thing we do with training is you define your neural net architecture, and then you run it with a parameter. You typically run it with Spark with parameter everything, or a parameter server with Spark, where you specify a couple extra knobs, and you go down from hours to minutes in the difference in training time.
Okay.
So you integrate with Spark, define your architecture, and you define your data pipeline, and you get run.
Okay. Regarding pipelines, are you planning to integrate with Spark ML pipelines?
We actually support Spark ML actually.
Oh, okay.
So in the recent release, we actually added Spark ML, and so we don't have a lot of pipeline stuff built in, but we have the Spark ML models in there.
Oh.
So the very basic Spark ML support is there. We'll add the pipeline stuff later. The problem is Spark ML pipelines are still very brittle yet though. Like for general purpose time series. For very complex vision pipelines, it's still very hard to do that, which is why we had to write our own tool to do that.
Okay.
It's getting better though, but they mainly support like academic data sets right now. But the real world doesn't have ImageNet. Like they start with ImageNet, but then if you have your own images, what do you do? And still, Spark is still a little restricted in that aspect. Yeah.
Okay. So usually I ask everybody, which I'm interviewing, how to start with the thing. So this book you have written and you gave it to me. Thanks a lot. So what are you covering in that book?
So basically, this is the book you want when you're an enterprise architect or you're an engineer and you're just coming back to the math. This is not the Ian Goodfellow book. Okay. Every time I see reviews of there's not enough math, I get frustrated because that's not the book. There's 10 books that do that. Right?
Yeah.
So if you want the math, go for the Goodfellow book, deeplearning4j.org. If you want the simpler book that's for engineers and focused more on applications, you go for our book.
Yeah, and actually, it's an advantage if there's not too much math in it, because otherwise you get just
So we have tables of just if you want an RNN and you want tuning, there's a table that says do this or that.
Oh, I see.
Yeah, so it's a lot more focused on concrete actions. And application building and integrations. And so we cover the basic neural net architectures. We have appendices on some of the more complex things like reinforcement learning, tuning, and other things in that general area though.
Okay. Cool. That's a good read for flying back to you.
Yeah. Appreciate it.
Okay, Adam.
All right.
Thank you so much.
All right. Appreciate it.
All the best.
All right.